What up, everyone? This is LeetCode 338 counting bits. So we're giving it integer n, and basically for every digit from 0 up to and including n, we have to, for that specific digit, we have to consider the binary representation and count the number of ones, right? So for 2, we do 0 up to, from 0, 1 up to 2, right? Um, right, 0 has, 0 has 0 ones in the binary representation. 1 is 1, 2 has 1, so our output array should be 0, 1, 1. We're just counting the number of ones for each digit's binary representation, and we're basically returning that as an array. Okay. Now, if I was given this question in an interview, I would solve it like this. Okay. I would just do a straightforward approach like this, which is not the most efficient or optimal, but I mean it is pretty simple. Pretty simple approach. So we'll do for num in range, right? N plus 1. So for every number, I would set the count to 0, right? That's it. The count is the number of ones that we're counting, okay? So I'm going to say while num is not equal to 0, right? I'm gonna and this number with a 1, and if it's equal to 1, we increase the count, right? Because if I have a number like this, right? If I and it with 1, all that's doing is returning 1. If our last bit is 1, it's going to return 1, okay? Now, if this last bit was 0, obviously it would return 0, so we wouldn't increment the counter. The way we handle the rest of these digits after we do this part here is we bit shift, okay? And the way I do that is by saying num is equal to num, right shift by 1, and we keep doing that while num is not 0, okay? So after that, we already have the count, so we're going to say answer append the count, and right out here we're going to return the answer. Okay, pretty simple. That's how I would solve it in an interview. The only problem is this isn't super efficient. There's a more efficient way you can solve it. And really, the efficient way to solve it comes down to understanding the relationship between every digit or every integer and its binary representation and how it relates to each other, right? So pay attention to the power of 2's, right? Right? Every section, right? For example, this is a section, this is a section, this is a section, this is a section, right? The sections are the powers of 2. So you'll notice, right, we have 0, 1, and then also here we have 0, 1. Well, the difference is this we have 1s here for this section. Right? What about here? We have 0, right? We have 1. We have 10. We have 11. What's the difference here, though? Well, they all have 1s here, right? Same here, right? We have 0. We have 1. We have 10. We have 11. We have 100. We have 101. We have 110. And we have 111. Well, the only difference here is all these digits here, instead of being 0, are 1, right? So it's an interesting pattern and relationship that we can observe. And it's kind of hard to observe this and understand if you don't draw out a table. I think the solution to this problem, the efficient solution, is a little bit hard to come up with on your own, to be honest. And really, the formula is, right, for any given number x, the array of x minus the power of 2 that we're on, right? Basically, the last power of 2 we encountered. So if we're at 13, the last power of 2 we encountered is this 8, right? So we do x minus that power of 2 that we're on. So for example, for this 9, this is a formula right here, right? It's really this, right? 1 plus the array of x minus the power of 2 that we're on. So for this, let's just do 10, okay? 10 minus what power of 2 we're on? We're 8. We're on 8, so 10 minus 2 is 2. So this should be 1 plus the array of 2. So this is the array of 2, 0, 0, 1, 0. If we add 1, it should be 1, 0, 1, 0. So yeah, 1 0 1 0. Now what if we do, I don't know, some random number, 15? Okay, 15. What power of 2 are we on? 8, right? So if we do uh, 15 minus 8, it should be 7, right? So we have 0 1 1 1. 1 plus 0 1 1 1 should be 1 1 1 1. Well, that's what it is. 15 is 1 1 1 1. Okay. Right, and we can do 13 as well, right? Should be 8 here, not 3, sorry. 9, 10, 11, 12, 13, so it should be 5. Index of 5 is what? 0 1 0 1. 0 1 0 1. So 1 plus 0 1 0 1 should be 1 1 0 1, right? Which is true. Okay, so yeah, this pattern is really hard to come up with intuitively if you don't draw out this table, right, to observe the relationship between the binary representations and the power of 2's, okay? So anytime we're going through any integer, right, we have to keep track of the last power of 2 we encountered, because we have to do, right, some digit minus the power of 2 we last encountered, okay? Does that make sense? Should make sense. Yeah, this problem is a little bit hard to understand because I feel like there's a lot of explanations that don't really explain the relationship that well because they don't draw this out nearly as well. But yeah, that's how you kind of, I don't know if I would say derive necessarily, but like that's kind of how you come to the conclusion that this is what the formula is. And it's really hard to come up with on your own. The solution to this problem, the efficient solution, is a bit hard. So I really wouldn't feel too bad if you can't come up with it on your own. I struggled with it as well. Yeah. So by the way, our constraint is n can be 0, right? So first of all, if n is 0, just return 0, okay? Because the binary representation of 0 is always going to be 0, 0, 0, 0, right? There's never going to be a 1. Okay, so let's create a array called dp of 0, or dp, sorry. This is what we're going to return. So we're going to do, we don't want to do 0 up to n because we need the index 0, right? That's why we do n plus 1. From 0 up to and including n. So we need n plus 1 indexes. Well, I guess 0 is an index, but you know what I mean. Like we need to account for the 0th index, so we do n plus 1. Okay. Now, there's no reason for us to do a base case like this because we already initialized dp of 0 to 0, right? So dp of 1, dp of 1, we set that to 1, right? So we're going to pick off from here. And the reason we do that is because we can keep track of what power we're using. And also the previous power, right? So we're going to say the current power of 2 that we're on is 2. The previous power of 2 is also 2. We actually are not going to do, we're not going to take care of the 0, actually. It's not necessary. So we're going to say for in range 2 up to n plus 1. Because we need to include n, right? So we do n plus 1. We're going to say if I is equal to the current power of 2, then the previous power of 2 is equal to the current power of 2, and the current power of 2 is equal to the current power of 2 shifted by 1. So the reason we don't want to start with this as the previous power or the current power is because we need to left shift this because every time we left shift this, notice how that's our next power of 2, right? Right? That's our next power of 2. But if we start from the 0, well, we can't just add a 0 randomly by left shifting, right? That's why we need to start at this 2. Because when we left shift this, right, our next power of 2 should be 1, 0, 0. And it is, right? 1, 0, 0. Left shift this, our next power of 0. Our next power of 2 should be 1, 0, 0, 0, right? After we left shift this one. And really, the reason this is important is what we're essentially doing is, okay, from when we're at this 3, we're using this as our previous power of 2. Okay, so we're doing, right, 1 plus the index of 3 minus 2, right? Okay, but the reason we need to, and maybe I shouldn't call this current power of 2. I should call it next power of 2, just so I don't confuse you. I apologize for that. Okay. The reason we need to care about this next power of 2 is because we need to know, like, for example, when we get to this 4, we don't want to be using this to calculate our previous index of, you know, I minus whatever the power is, right? Because when we do 5, we don't want to do 5 minus 2, we want to do 5 minus 4, right? That's why we need to keep track of what the next power of 2 is and what the previous power of 2 is, okay? So we'll do dp of I is equal to 1 plus dp of I minus the previous power of 2. I know these variable names are really long, but I don't know, I just want to make sure you kind of understand what's happening. Okay, so I didn't change the variable name here, my bad. Oh, same here. Yeah, I'm just changing the variable name just so you're not confused. Okay, so again, with these two variables, the point of them is that, right, if we're at this 7, right, we want to do 7 minus 4, right? Because again, this is our formula, right? It's I minus, you know, last power of 2 we saw, right? If we're at the 7, we want to do 1 plus dp of 7 minus 4, right? But when we get to this 8, right, we don't want to do 1 plus, or this 9 too, right? When we get to this 8, we want to update this last power of 2 variable, right? That's why we need to left shift it so that we know when we have to change it, our previous power of 2, right? Because when we're at this 9, for example, we don't want to do 1 plus 9 minus 4. That would give us the wrong answer. We have to do 1 plus 9 minus 8, right? So this really is just changing, it's important to change this variable. Yeah, this part right here is really, really important, just so we can change this previous power of 2 we've seen. But we also have to change the next power of 2 so we know when we have to change this one. Okay, does that make sense? I think it makes sense. All right, just think about it logically. We're just updating the last power we've seen, and when is the next power that power of 2 that we're going to encounter, right? So we can update our previous, when we encounter the next power of 2, we need to update our previous power of 2, so that our calculation still works. So yeah, that's what this part is doing, in case you were confused. That's why we're left shifting by 1. And that's also why we're setting this to 2, and we're starting at a power of 2. Or we're starting at the integer 2, sorry. Because when we left shift by 1, right, every power of 2 is left shifted by 1. Notice that? But if we start at 0, we left shift by 1, we're still gonna have 0, right? So it's not gonna it's not gonna work. Okay. So yeah, this is a dynamic programming solution. Dynamic programming is a bit hard. This problem was honestly a little bit hard for me to understand at first. The efficient solution was really hard for me to understand. Yeah, in an interview setting, I would probably use the solution I showed you at the beginning of the video, because this is a little bit hard to come up with on your own, if you don't have a lot of experience with dynamic programming. But yeah, there's a lot of good videos out there on this problem, particularly a guy called I think LeetCoding with Sam. He's the one who really helped me grasp this problem, so shout out to him. Let me see his channel name. Sorry. Oh, his name is Sam Does LeetCode. He's like he is a ex Google and an Amazon senior software engineer. Yeah, he has a YouTube channel on here. He helped me grasp this problem a lot, so shout out to that guy. And yeah. So anyways, I hope this problem was useful. I showed you the kind of brute force approach I would naively use at the beginning, but this is the efficient solution. So yeah, hope it helps, and I'll see you in the next one.